Hello and welcome to the intro class, Communication Sciences and Disorders, the intro to ComD. We are going to speak about some basic sciences, and this is based on Gillam 2016, Communication Sciences and Disorders. So in this chapter, we'll speak about the sciences that have to do with communication, and as you notice in the undergrad programs are called usually communication sciences and disorders, because you study like anatomy and speech and hearing and so on. So this is just a very superficial survey of the sciences and disorders of speech and language. So it is not deep, it is not in depth by any means, and each component, each major component of this chapter, that is basically a summary of an entire course. So you'll be taking courses in anatomy and physiology, for example. You'll take courses in a course in neurology. You'll take a course in, language acquisition and so on. But this gives you just a, kind of a flavor of what the sciences of communication sciences and disorders are. So we'll speak about the structures and functions, or basically the anatomy of the nervous system, and also for example, how there are certain areas in the brain that are dominant for language and make language possible, or make communication, speech, language, and communication generally make it possible. You look at the respiratory system and the phonatory system, and also speech articulation. In communication sciences and disorders, generally, we focus on 5 systems of the body that enable us to communicate. And the body has many systems, of course, but 5 of them are interacting together to make communication possible. The first system is the nervous system, and that is basically the brain, spinal cord, and the peripheral nervous system, the nerves that come out of the brain and the spinal cord. So that is the nervous system. And without it, you cannot do anything at all. Nothing at all. You cannot smile, you cannot talk, you cannot walk, you cannot think, you name it. Without the brain, without the nervous system, there is nothing possible. So then we have the respiratory system, which is basically the outcome of it is to fill the lungs with air. and then as the air is exhaled, then we valve it with the vocal folds, and then the pressure, we use the pressures as the air is exiting in order to generate a buzz. We call that buzz produced by the vocal folds, we call it phonation, or we call it voice. So that buzz, simply just a buzz like ah, that buzz, as it exits and it goes into the vocal tract, it becomes shaped by the articulators, we could say chopped, into sounds and words and sentences. And we call that speech articulation. So then you have spoken, and you need to send your message to someone else, and for yourself to also hear your message. So the auditory system is the system that enables us to receive and to comprehend and to process spoken messages. And these spoken messages, as they go into the auditory system, they cannot be understood, they cannot be comprehended or processed without the brain. So it begins with the brain and it goes back to the brain again. So this is what this lecture is about. So the nervous system, there are two ways to look at it. First, in terms of the anatomy, we divide the nervous system into the central nervous system, that's the brain and the spinal cord, and then the peripheral nervous system, that is all the nerves that come out of the brain stem and out of the spinal cord. Basically, you can think of the body as just say a robot, and you want to make this robot move and do, talk and do things. So you build the hard drive here, and out of that hard drive, you get all these wires and cables, bundle them down, send them down into the spinal, what is similar to like the spinal cord, down. And then out of this big cable, you take branches out, wires, and send them to any area that you would like to move. You want the robot to move a finger like this, you have to send a wire to, and you send electrical impulses from here to the finger to move it like that. So simply, that's what the nervous system is about. Again, the brain is the central component. The spinal cord is part, also like the tail of the brain, which is all a bunch of pathways going up and down. And out of these two, you get the nerves that come into your thorax and your legs and your arms and so on. So that is the central nervous system and the peripheral nervous system. The nervous system generally is made out of three kinds of neurons based on function. Remember, function means physiology. Function. Any neuron in the nervous system can be one of three. Number one, it can be a motor neuron to move things. Number two, another kind is sensory neuron. That is the neuron that brings signals from the body, from outside of the body or inside of the body up to the spinal cord and the brain so that these signals can be processed. And then the motor neuron and the sensory neuron cannot function. The motor neuron cannot function, cannot do its job if it is not connected to the sensory neuron. So the sensory neuron and the motor neuron are connected together with a little, with a neuron that is specially designed for that. That is called the interneuron. It's like between neurons. It's like national, international, between nations, or on the level of nations. So, take for example this. The knee-jerk reflex is mediated by the spinal cord. This is a slice. This is a cross-section of the spinal cord. And so you have now the nerve or neuron coming connecting on the muscle, the femoral muscle, on the muscle in the femur, and that muscle is the one that activates your knee. I mean your leg. So there's a tendon that connects that muscle to your knee cap here, and then that is connected to your leg. So when you tap this, the muscle will contract and it will pull that tendon, and the tendon will pull the leg up with it. As you can see in the arrow, that's the same leg, but once you tap, the leg will jerk. So the reason it does so is that the sensory neurons are connected on the muscle fibers, and when the tap goes, if someone taps it, the sensory neuron is going to pick up the signal that shows that something is displacing the tendon, and that signal is going to go up and travel through the sensory neuron to the spinal cord. In the spinal cord, the motor neuron that goes back to move the muscles of the femur and to make them contract and pull up the leg, this motor neuron has to get input from the sensory. So you have to connect the circuit. So that green neuron here is the interneuron. So these are, again, based on function, not on anatomy, because there's more than 100 kinds of neurons, different shapes and different, sizes and so on. But in terms of function, you have the motor neurons for the transmission of motor signals to move structures of the body. And then these sometimes are called efferent. They produce an effect. And then sensory sometimes are called afferent. Afferent means you don't move structures, but you send sensory signals like hearing, like for example, when you feel heat on your skin, you feel like, say, the wind moving your hairs. This will send afferent signals or sensory signals from the skin, into your arm and through your spinal cord, and that will reach the brain at some point. And then we have the interneurons. So most of the basically the tissue of the brain and spinal cord, they rely on the interneurons to connect motor and sensory neurons. And then the brain, in order for these neurons to move, to send signals and to process signals, they use neurotransmitters. So neurotransmitters are small chemicals. For example, dopamine, for example, is a neurotransmitter. Nicotine, for example, the melatonin is a neurotransmitter. So these are chemicals that go on a channel on the membrane of a neuron, go on a channel and dock like a lock, like a key to a lock. And once they dock on the surface of a channel, that channel is going to either open to allow certain chemicals to go in and to bring the signal in, or it is going to make a channel close so that it can stop the cell, or can inhibit the functioning of the cell. So these are again called chemical messengers or neurotransmitters. You can see the neuron here. This is a model of the motor neuron. We do not see the myelin. The myelin usually, so you have little segments like marshmallow, small marshmallow segments here, kind of distributed here throughout the axon. But between one piece of myelin and the other, there's a tiny gap, that actually is very important for the transmission of the signal. But just these are the parts of the neuron. the soma, or the cell body, and that is where the cell signals are processed, where the DNA resides. When important work is done to make the DNA to reproduce, cells and parts of the neuron, to maintain its health and to maintain its function and to produce neurotransmitters and so on. Then, on all along the body of the neuron, there are branches called dendrites. Dendrite is a branch, means branch. So dendrites. These dendrites have numerous sites, where every site is shaped like this, and it can make connections with another neuron like this. So they make a synapse and they receive signals. Dendrites can only receive signals. They do not send signals. They receive signals from another neuron or from the environment. So then we have connected to the body of the neuron is that little thread, or we call it the axon. The axon. So the axon is it goes from the body to the end, where it branches into little branches called telodendrites or telodendria, or better and more common, they're called synaptic terminals. So this whole branch here, you can call it a synaptic terminal or a telodendrite. So the function of these synaptic terminals, when you look under the microscope and see one, it's like a foot. So, or, shaped like a foot. And it goes to where the dendrite, end of a dendrite is shaped like this. And then the axon terminal goes like that. And then between them, there's a little gap. So these two pieces together and the gap between them, they are called the synapse. And this is where the cell that is sending a signal, through the synaptic terminal, is going to release neurotransmitters into the synaptic gap. And that is the neurotransmitters are going to dock onto channels, receptor channels, all along the surface or the membrane of the dendrites. And then they can open the channels or close them to send the signal down to the cell body. And the cell body, processes it, and then it decides if that signal will be refired again. If it is refired, this part here, called the axon hillock, will fire the signal, and it's going to travel through the axon, and then it will be sent through all these synaptic terminals to other neurons. So other neurons will receive it through their dendrites, and these dendrites go again to the same thing, cell body, and then the axon of the other neuron. And this is where you can make a chain, basically sending a signal from one neuron to the other, to the other, to the other, and it goes very, very fast. So again, the part that you are not seeing here on this neuron are the little segments of myelin, and they go all over the entire axon, but in between each segment of myelin and another, there's a little gap called the gap of Ranvier. But you'll find it in your textbook. I wouldn't go deeper into this because they're gonna have anatomy and they're gonna have neuroanatomy as well to go deeper into these things. So back then, we have neurons. When we look at the cellular structure of the nervous system, we have either neurons in terms of anatomy. Now we looked at the function, but in terms of anatomy, we have either neurons or we have other cells with them that are called glial cells. The term glia comes from the Latin word glue. Glue basically comes from glia. So it is like sticky kind of cells that clump and kind of make a sticky kind of structures around the neurons, and they cushion them and they feed them and they make without them the neuron cannot function. In other words, if there's any abnormality in any one of these kinds, that is not gonna function. The neuron will not be able to function. So for every neuron, there is about 10 to 50 glial cells. That is the ratio. Glial cells are smaller. They do not, I mean, for the most part, they do not transmit signals, but they make it possible for the neuron to transmit signals. So we'll speak about only a few of them, different kinds of glial cells, and we'll mention like the function of each in just maybe a sentence or two. So you notice here, this is one cell called the astrocyte. Astrocyte, it means star-shaped. Astro means star, and cyte means cell. A cell that is shaped like a star. This is the cell that makes the blood-brain barrier. The blood-brain barrier, if you look carefully here, you'll see like there are little, pods, little feet kind of. Every branch here of the astrocyte has a little foot called pod. And all these, the branches, they go and dock onto a blood vessel and connect and synapse, and inside of the pod and the blood vessel, there are channels where the nutrition that is needed by the brain, by the nerves, by the neurons, the nutrition from the blood is going to be selectively taken in through the blood-brain barrier. We call it barrier because not everything can go through. It is only selectively taken because there are many substances in the blood that can damage and kill the neurons. So then, the astrocytes extract the nutrition from the blood and process it in their body, and then send it on the other side to neurons, where they connect, also have pods connecting onto neurons, and they send the food to the neuron this way. This is how the neurons are fed. So that is the astrocyte. Very important it makes the blood-brain barrier. And you can look at some medications, for example, like ADHD medications or psychiatric medications. You say, usually they say if the medication penetrates or goes through the blood, crosses through the blood-brain barrier. You look on the left. You see that is a modified white blood cell. Basically, it is called a microglia, and this microglia is a modified white blood cell that is part of the immune system, and it is smaller than everywhere in the body, because you want it so much to fit into the brain and the spinal cord. There isn't much space, so that is modified. These are the cells that they look for when there is, they do a spinal tap. For example, when there is an infection, encephalitis or meningitis, they do a spinal tap where they draw fluid from the spinal cord, and if they look at how many of these white blood microglia are there, and if there are more, it means they are fighting an infection. So the microglial cells are part of the immune system, and they're responsible for maintenance, removing debris, destroying pathogens that come in, invaders like bacteria and so on, and recycling them. So they are critical for the health of the nervous system. Then we have other cells, like this is called oligodendrocyte. That cell is one of two kinds that make myelin on the axons of neurons. So you can see there's an axon, and there's another neuron that has an axon, and this cell can have so many branches, it can myelinate multiple neurons, and this is called oligodendrocyte. And that cell only exists in, it myelinates the axons only in the brain and the spinal cord. But another kind that makes myelin for motor neurons, like here, for example, in the peripheral nervous system. That is called a Schwann cell. It wraps itself like a piece of marshmallow around each segment of the axon, and multiple Schwann cells are required for one single neuron. The biggest neuron will take about 400 segments of 400 Schwann cells. Each one makes a single segment of myelin to myelinate the axon of neurons in your arms, in your legs, in areas of the body that move, or nerves that come out of the spinal cord or out of the brainstem. So in general, one kind that I wanted to mention here, glial cell, this is the purple line here. These are called radial glia or radial glial cells. They are shaped like a cylinder, like, one piece shaped like a little tube. And then you get many of them coming together and connecting with each other like this. So you get so many pieces, then they make like a hose. So that hose, for example, it goes from the site where nerve cells are born. During development, nerve cells are born in a tiny area called the neural crest. And then neurons are born at the rate of 250,000 per minute. And they keep just traveling. So you have deep in the core here, the neural crest, you have a neuron, for example, born. And then you have one of these wires here, one of these hoses made out of radial glial cells, extending from the site where the neuron is born to the site where the neuron should be. And as the neuron is going to cling onto it, and it's going to travel. So you notice here, the neuron is just born. It was just made. And then it clings on it, and as it goes onto the glial cells as a guide, it knows where it is going, and it gets nutrition, and by the time it reaches its destination, it is already a mature neuron. And it knows exactly where it is going to be, if it will be part of your hearing, part of your cerebral cortex, part of your motor system, and you name it. So without the radial glial cells, neurons would not be able to find their destination, and any disruption of the migration process due to microglial cells will produce devastating damage. Okay, so now we spoke about the cellular structure of the nervous system quickly, just very, very quickly. Now we're going to look at the anatomic structure and for bigger areas of the nervous system. So we said that the nervous system has two big anatomic divisions. One is called the central nervous system, and the other one is called the peripheral nervous system. So the central nervous system consists of the brain and the spinal cord. Spinal cord is just like the tail of the brain and continuous with the brain. I wanted to find an image. Okay, so Now, look at this. You have the spinal cord here, and above, as you enter the skull, the spinal cord continues, but as soon as it crosses the skull, we call it the brain stem. So the brain stem goes just about here, 11, yeah, just about here. And then you go up, that is the medulla oblongata, part of the brain stem, and the pons, that is part of the brain stem, and the little piece above the pons, that is called the midbrain. All these three areas, medulla, pons, midbrain, make the brain stem. On top of the midbrain, there are two little structures called the thalamic nuclei, and they are right in the center of the brain. You do not see them clearly here. You do not see them. So what I am saying is, these areas here, they make the primitive brain. They make your body basically run itself. Like you breathe, your heart beats, and so on. And so once you take these, anything that goes above these, all of this structure that is convoluted here and there, all of this, that is called the cerebrum. See, all of this is the cerebrum. This is all you see outside here. This is the cerebrum. So again, if you take the brain stem and the thalamic nuclei deep inside there, and the cerebellum out, everything else, all of this is called the cerebrum. So the cerebrum has white matter inside, deep, and it has gray matter. So basically the gray matter lives on the top, very tiny cover of the entire, brain that you can see here, folded and convoluted. That is 4 millimeters thick, 4 millimeters thick, very, very small. And it is folded and convoluted, and it makes like areas that we call sulci, and areas that go up like mountains, we call them gyri. So that top layer, this is where the bodies of the cells reside, here on the top layer. And that is why the bodies of the cells of the neurons have lots and lots of oxygen, glucose, and so on. And the color of the bodies are gray, so gray. This is why we call that top layer, the top surface of that, we call the cortex, comes from the Greek word tree bark. So that is the cover. And that is the most important structure that makes us human, basically. That thick. So the gray matter. So a cell body, say, would reside here, and then it will send down its axon, and all these hundreds and millions of neurons send down their axons. So again, the gray matter, cell bodies, and then as you go down, these little threads that are insulated with myelin. Myelin is white, and this is why all these wires are called the white matter. So all of this here is the white matter. All of these are the axons coming out and, connecting. And you have one hemisphere now, one hemisphere, and another hemisphere. So we have right and left hemispheres. In between them, these hemispheres are connected with a structure that you could see here, where all these neurons come in and just are compressed and bundled together so tightly, and they connect the right hemisphere with the left hemisphere. That area is called the corpus callosum. Corpus means body, callosum means callus, tough. So that's the corpus callosum. It is the biggest bridge, the biggest pathway that the brain uses to send signals from left to right and right to left. That is the corpus callosum. So the cerebrum, again, has a right hemisphere and a left hemisphere. The two hemispheres, the two sides, are similar in structure, similar in anatomy, but they are not symmetrical. They are not similar in function. Each one specializes or is dominant for a specific set or a specific type of functions. So, and the reason is you do not want the two to do the same job. So what is the use of that? You want to create diversity in the brain. Each part will be responsible or will be dominant for a big function, and the other parts will help. But this way you can do a lot with a little. So all these structures, small structure, 3 pounds, it changes the face of the earth. I mean, that is how it is, how powerful it is. And that is, again, because every part of it can do so much, and you don't have redundancy. You don't have two parts of the brain doing exactly the same job. So the cerebrum has left and right hemispheres, and then deep inside of the white matter, there are clusters of cell bodies buried deep. They are called the basal ganglia, and these structures basically connect the cerebral cortex with the lower parts of the brain, like with the brain stem and the spinal cord and so on. The basal ganglia. And then the thalamus, I told you about it. If we come across an image, I'll show it. So, again, it has the gray matter and the white matter. And now, when we look at the cerebral cortex, we know, we want to know landmarks. I mean, it is divided into particular landmarks based on the bones that cover them. So here, from this line here, forward, this area is called the frontal lobe of the brain. I'll give you some basic functions, to list them so that I need you to know them. So the frontal lobe of the brain it has the centers for movement, voluntary movement, and of the body here. And also it has planning for movement. So that area here that you could see these little wires coming from, that area is called the motor cortex or the motor strip. That is part of the frontal lobe. And then in front of that, so that whole area has a map of your body, and every part of your body has a piece here that actually, a set of neurons that actually move it. So here, for example, are the areas that move your face and your tongue and your lips and your neck muscles and all the areas for speech and swallowing and so on here. And then as you go up, you go your hand and then your upper shoulders and trunk and this and all the way until you go between the two hemispheres. Then it continues between the two hemispheres. And then the motor planning areas. And then in front here, you have work and memory, you have decision making, you have judgment, you have executive functions of the body, you have attention skills, and you have all kinds of functions that basically enable you to run your life. It enables that body to run it, to run efficiently and to make decisions and to regulate emotions, regulate communication, visual processing, and you name it. Very, very critical. Then here in this area here, where kind of the crown of the head here is called the parietal cortex. This is the sensory map of your body. It has a sensory map of your body, and it is critical for writing, for reading, for movement, for sensory sensation from the different parts of the body, whether you are moving or whether you it gets signals for pain or temperature, whatever it is. So that is your parietal cortex. And then the back here is called the occipital lobe, because it is covered by the occipital bone. And the function of this lobe is vision, visual processing, and visual memory. So it receives images from the eyes, connected directly to the eyes, and it receives images, and it also enables you to move your eyes left and right, up and down, at an angle, and so on. And to process, visual images, and to give you the different senses that have to do with vision. Vision has more than one sense, has several senses. But we don't get into them now. And then we have this lobe, or the word lobe equals the word cortex, or piece of cortex. So this is called the frontal cortex or the frontal lobe. The parietal cortex or the parietal lobe, occipital cortex or the occipital lobe, the temporal cortex or the temporal lobe. So that area here is critical for communication, for processing auditory messages, for memory, and for emotions, for learning. It is very, very important, and this is, for language. So there are two other, so we have four lobes or four parts of the cortex, and we have two more that are buried inside that you do not see. So the cortex really has 6 parts, but because these are the ones that you can see easily in the front, people just know them all. But there are 2, I'm going to name them, but you are not required to know them. If you pull this area down and this area up, you will discover an island hiding under here. It is called the insula, or the insular cortex. And that is also part of the cortex. If you take the 2 hemispheres, pull them down, or open them up, you will find that there's a structure called the cingulate gyrus that is buried between the 2 hemispheres. So these 6 parts make the cerebral cortex, okay? And the cerebral cortex is only the top layer of the cerebrum. This is why, it has to do with the cerebrum. This is why I call it cerebral cortex, or the cover of the cortex, of the cerebrum. Okay. Now, then we have the cerebellum. The cerebellum is in back of the brain, and inferior, back and below, behind the brain, and back of it, and it has also a right hemisphere and a left hemisphere. It is very important for motor processing, for sensory processing, for language functions, for swallowing, for many functions. But it does so much with motor coordination and basically correcting movements and comparing what you want with what your muscles are actually doing. For example, you have an intention here. I want to wiggle, move my finger this way. If you are doing it right, then the cerebellum is going to take sensory information from the joints to show exactly how the finger is moving. And it looks at the map of your command, the map of what you want, and it compares the 2 together and says, okay, this is what you want, this is what is happening on the ground. If there are any errors, it will point them out and send you feedback here so you can correct your errors. And we do, of course, this applies to speech and so on. The brainstem, this area here, the medulla oblongata, the pons, and the midbrain hidden inside here. This it is responsible for primitive functions. And these functions basically enable you to survive. You can breathe, your heart can beat, you can digest, you can do basic reflexes and so on. But it basically, it is the most primitive part of the brain. It is the survival part. It has a lot of autonomic functions that enable the body to run itself. And all the structures above it, and the cerebrum, these are the ones that actually enable us to do thinking and to do all kinds of mathematical calculations and cognition and all of that. The spinal cord, again, you think about it, basically the whole idea of the spinal cord is that it's a bunch of pathways coming down to bring motor information, motor commands down to the rest of the body, so you can move arms, legs, and your body. And a bunch of pathways or cables, if you will, that come from below and bring sensory information from the lower parts of the body. That's the whole thing. It's about wiring. So ascending means sensory pathways, and descending means motor pathways. So you make a decision, you send down the order so you can move your lower body parts. And then you receive sensory information from that. You bring it to the spinal cord, to the brain stem, and the brain. Okay. All right. So the left hemisphere and right hemisphere, I need to clarify that in the past they made a big deal out of it. Nowadays we know that there's no one who call, oh, that person is a right brain, this person is left brain. That's now a myth, because the left hemisphere has to rely on the right hemisphere, and the right hemisphere has to rely on the left hemisphere. They both have to work together to make you a whole human being. So that, I'll give you a quick example. So, say, for example, you hear a sentence. Say, it is raining cats and dogs. As you hear that, the signal comes, say, from the right ear, goes directly to the left hemisphere. This is where your lexicon, your mental dictionary is, your grammatical rules, are there, and your phonemes and the sounds. So that is dominant for components of language, building blocks of language here. So when you hear, now the signal also comes from the other ear, goes here to the right hemisphere. And then, now the right hemisphere hears the sentence. It is raining cats and dogs. And the left hemisphere hears it. So the right hemisphere now cannot get the meaning of the words, cannot recognize the words, cannot get their meaning, cannot make the sentence structure. So it gets the signals, yes, here, but it has to communicate with the left hemisphere to get the meaning of these words and sentences, to assemble the sounds, like, it, z, you have to assemble these sounds into syllables and words and so on. So the right hemisphere has to rely on the left to get the raw material. Okay, so then the left hemisphere is the one that's going to do the interpretation first. Oh, it is raining cats and dogs, and it literally takes it. Okay, go outside and look at the cats falling down and the dogs falling down. That is what the left hemisphere do. But the right hemisphere is going to say, no, that is not what it means. You stop that interpretation, and I have an interpretation here, a meaning that is based on the entire sentence. When you put all these words together into one saying, an idiom, that is what it means. Even though there is nothing in the sentence that says it is raining or it is raining heavily, now the right hemisphere takes the whole context and it gives you that meaning. So the left hemisphere is dominant for sequential functioning, like mathematic skills. Dominant for language, for speech and language, and it has the lexicon. It stores the lexicon of the words, mental dictionary, and it also has areas that process grammatical rules, and assembling words, sounds into words, and connecting words into meaning, into the meaning of the concept, and then sending that to the another part here, and then communicating that to the right hemisphere, so you can get a whole understanding of what you hear. So the right hemisphere is responsible for holistic processing. Like you listen to a story, read it sentence by sentence, and then paragraph by paragraph, and then you come and then say, what is the connection? Why is this? All these paragraphs are connected together to make one story. What is the idea of that story? So that is the whole picture. The whole story is about this or that. The right hemisphere is what integrates different parts into a whole and enables you to see the meaning of that whole. It is dominant for facial recognition, recognizing faces and emotions, and comprehending, again, emotion. There are two aspects here. So in addition to facial recognition, recognizing if you are sad, happy, angry, whatever, there are two areas in it. One area in the front here, in the frontal lobe of the right hemisphere, enables you to put the right tone of voice that matches the meaning of what you want to say. So you want to show happiness by the tone of your voice. You want to show if you are going to ask a question by the tone of your voice. You want to show if you are sarcastic, if you are whatever expression, emotion that you want to express, that area can enable you to match your facial expressions and the tone of voice with the meaning of what you are saying. Now, there's an area back here, like on top of the right ear and the right hemisphere, temporal cortex. That area enables you to comprehend the tone of voice of someone else's speech. So this is where you understand, is that person mocking me? Is that person really happy for me? Angry, sad, and so on. So that area enables you to comprehend the tone of your voice, of someone else's voice. Okay. So again, even though they look the same to you anatomically, mostly the same, in terms of function, they have asymmetric function, means each one performs or is dominant for a certain kind of function. We are going to look at a few areas that have to do with language. I'd like you to know this is the left hemisphere. I'd like you to know that this area here, there's a belt area here in the left hemisphere. Basically, see this line? This line here is called the temporal fissure or the Sylvian fissure. Let's say for now we can take the temporal, because the temporal lobe and the fissure above it, it divides it, separates it from the frontal lobe and from the parietal lobe. So that fissure, around that fissure, here and here and here, like a belt area here, that is, all of these are language areas that enable us to assemble speech and to make language and to express that language. One area of interest here, I'm going to go first with Wernicke's area. Wernicke's area is on the temporal lobe. I need you to know where these areas are. On the temporal lobe here, the superior gyrus, on the posterior part of the superior temporal gyrus. That area is called Wernicke's area. Wernicke's area is connected to the auditory cortex. It is connected to an area here called the auditory association cortex. And in the end, so when you say something, you hear something, it comes and say cat, ka, t, and now you don't know what that is. So that comes from the primary auditory cortex, and then it goes to Wernicke's area. So Wernicke's area takes it and puts the sounds together, assembles them. Oh, cat. And then say cat. What is that? So Wernicke's area communicates with these areas here. Behind this area, deeper, you find the memory center called the hippocampus. And so in the end, the hippocampus it can access all memories you have on the cerebral cortex. So you say, cat, what is that? And then finally, the areas here, the auditory association cortex, and it works with the memory center, the hippocampus, and they get you the meaning of that. What is cat? So you associate the sounds of cat with the meaning of the concept, and that is sent to Wernicke's area. Now you have the word and the meaning of it. Now you send that forward. There's a special pathway that connects this area with another area here called Broca's area. And the frontal lobe, inferior, posterior part of the frontal lobe. So this pathway, Wernicke sends the word, and Broca's area says, oh, that is a noun. Actually, it can serve like this. It needs the before it, or it needs a before it. It can fit as a subject, or it can fit as an object in the sentence, and so on. Because Broca's area is the sentence processing area, grammatical processing. So it sends the feedback again back to Wernicke's area. The connection between these two areas is called the arcuate fasciculus, the arched pathway. The arcuate fasciculus. Fasciculus means pathway. So then, now, you have the meaning of the word, and you know how to use it grammatically. What is it, a subject? Is it a verb? Is it a verb? Is it an adjective? And so on. And then now you send all of this to the frontal lobe of the brain and say, now I have the meaning of this and that. What do I do now? And then you decide if you are going to say something back, if you're going to answer a question, and so on. So Wernicke's area is dominant for recognizing speech and assembling speech and associating speech with meaning, which means understanding auditory information, and sending the information to Broca's area. Now, Broca's area has two functions. Two major functions. First one is that it serves as the area for grammatical processing. It enables you to have the grammar of the language. All your grammatical rules are there processed and made there. And even if you have multiple languages, all of them are processed here. So that is one, grammar. And then the other function is to activate the motor cortex. That's motor cortex. To activate the parts of the motor cortex that enable us to move our lips, our larynx, all the speech, basically speech. So it enables us to make, to help us to make a script of what we want to say. And after a lot of processing and working with other areas here, then Broca's area sends the information to the areas here to move your muscles of speech so you can say the word. So it has motor programming, not activation, motor programming. The activation comes from the primary motor cortex itself. So if you will, this Broca's area, it sends the information to the motor cortex, and then Broca's area becomes quiet. Okay, here you go, throw the ball, and then you become quiet. And then the primary motor cortex then is going to activate the muscles directly to make you make speech. So the primary motor cortex, as I mentioned earlier, this is the area here, that pink kind of strip here. From here to the front, that's the frontal lobe. That is part of the frontal lobe. And so sometimes we call it the precentral gyrus. Because of its function, we call it the motor cortex or the motor strip. If you have a transverse cut here, you can see through, for example, the tongue. All these neurons process signals to move the tongue, have to do tongue movement. And then the axons go down, and the signals go down through the axons until they reach your brain stem. Out of the brain stem, there are nerves that go out and connect with your tongue, with your lips, and so on. So every part here, the eyes, for example, you have, they move by this area. This area here is the hand. So all these neurons move, the hand in different ways. Here you have the torso. So that image here is called the homunculus. Homunculus means little man. So there's a motor homunculus, which shows the map of motor movement, voluntary movements, and the sensory homunculus, that is on this area here, because that's part of the parietal cortex, and that is a sensory map of your body. So for example, here you have, in this area here you have the sensation from the tongue movement, or if there is pain, or if there is heat, or you eat something that is spicy, all of that is felt here. So, and in here, the tongue movement. And you go, say, lips. The lips are here, moved by this area. And this area gives you the sensation from the lips as they move, and so on. Okay, so these were just highlights, only highlights of some of the structures. Now, of the central nervous system. Now, the peripheral nervous system basically consists of all cables, all nerves that make that branch out of the spinal cord and the brain stem. Inside of the skull, along the brain stem, I can show you from the beginning. Where is it? Here. So the brain stem, along it, inside of the skull, you have origins, you have roots of 12 cranial nerves. We call them cranial nerves because they originate in the spinal cord, but they go out of the spinal cord and they go, for example, to your skin, your face, to your neck, to your shoulders, to inside of your trunk. So they are called again cranial because their roots are inside of the cranium, and then they go out and move the neck and the inside of the mouth and pharynx and facial head, all of this basically to wire all these areas inside and out. And then some of them, one nerve goes out to move your shoulders, and one goes down to innervate all the inside of your trunk. Like your lungs, your intestines, stomach, and so on. And these are numbered from 1 to 12. And of course, there are 12 on each side. So we call them the 12 cranial nerves because their functions are identical. Right hand is the same as left hand in terms of anatomy and function. The same here for cranial nerves. So in reality, they are 24 if you count left and right. But we typically say just 12 nerves. That means on one side. So we'll give you just some kind of an overview. The ones, for example, that can have to do with speech, for example, the trigeminal nerve. Trigeminal. Hold on. Tri means three. Geminal Geminus means twin. So it means like the three twins, the nerve that's like three twins. It comes out out of the brain stem, and it just goes to the face like this. One branch goes to the jaw area here. One goes to the area here called the maxillary area and the nose. So like this. And another one goes to the area of the forehead. So all of these are innervated, like when I am able to go like this and that, because if these go like this. So all these moves, and it has sensory and motor. So, and the other ones go like this, like that. So if you make a line in the center, then this side is innervated by this nerve, by these three branches, and this side by these three branches. And when you look at each, these are twins, these are twins, these are twins. So trigeminal means the three twins. And then, so the trigeminal, has motor functions. For example, enabled us to chew food. It has also sensory functions. For example, it gets sensation from the face of the skin of the face, and also the upper teeth, and from the eyes, sensation. And then we have the facial nerve. That's nerve number 7. If you look here, number 7, and that where is it? This one. 7. They go from top to bottom. So the facial nerve has motor functions, and also it enables us to move our facial muscles, for example, smiling, puckering your lips and rounding your lips and so on. And it also has sensory functions, it gives you sensation from various parts of the face. We also have the this cranial nerve number 8, which has to do with hearing, and that is called the vestibulo-cochlear nerve number 8. And that that's what enables us to get hearing and also balance. Vestibulo-cochlear nerve. So hearing and balance, and you'll study this in detail in anatomy and also neurology. The vagus nerve, as you could see, the vagus nerve comes out of the brain stem and travels through the neck. It actually innervates our vocal folds. We can talk, there are branches from it that enable us to vibrate the vocal folds and move them, bring them together to phonate and make sounds. And also different parts of the pharynx as well, and the soft palate. And then it goes down into the trunk, and it innervates all the internal structures, even your diaphragm, your liver, stomach, intestines, kidneys, you name it, all of these areas. It's the biggest nerve. It's called the wandering nerve. Vagus means wandering. So it has motor functions, for example, for intrinsic laryngeal muscles that move the vocal folds and adjust them, make high pitch, low pitch, pharyngeal movements, like when you swallow, when you cough, when you swallow, you notice that your pharynx is going to be constricted and then again dilated again. It has sensory motor functions for abdominal, visceral structures, like it enables you to digest, enables your heart to beat, your lungs to breathe, and your intestines and to work. And then we're just highlighting some that are significant for communication and swallowing. And then the hypoglossal nerve. Glossus means tongue. Hypo means beneath or below. Hypoglossal means the muscle, the nerve that moves the back of the tongue. So, the base of the tongue, basically. It comes and inserts onto the into the foundation, the lower structures of the tongue, and it can. So the hypoglossal nerve, enables us to get different motor movements, from the tongue. Okay, that's enough for the cranial nerves. Again, you'll study them in depth in anatomy and physiology and in neurology. And then we have a structure called the pyramidal tract. When you go back here, this is the motor cortex. And out of the motor cortex, we said we have a map that moves different parts of the body. Then all of these these cables, big bundles of them go down. As they go down, you are going to establish a pathway that goes down through the brainstem and the rest of the spinal cord. So that pathway here, it comes from different areas, and as it goes down, shooting, going down, for example, it makes something that's called the pyramidal tract. It's motor. And then there's also part that is called the extrapyramidal tract. They are responsible for movements. So the pyramidal tract is a direct pathway that goes from the cortical neurons here on the motor planning and motor cortex and sensory cortex, go down directly to the peripheral nerves. You go down to the spinal cord, and that connects with all the roots of the nerves here. And then the extrapyramidal tract, it's more complex. It is responsible for like fine-tuning movement. And when you have complex movement, you are able to control these movements. It's more of an indirect. It kind of loops around, the areas of the basal ganglia. And this is why the basal ganglia have to do with coordination of movement, with regulation, with refinement of movement, like fine motor. So these pathways, again, enable us to perform accurate movements. We have different mechanisms. Technology has, of course, advanced significantly, and we are able to study brain structures and functions using, for example, CT scans, MRIs, PET scans, and more importantly, there is a kind of scanning called fMRI, functional magnetic resonance imaging. That is, you have electrodes, and then you read something or you say something, they give you a task, and they show live what the brain is doing while you are performing functions. Like communication or memory and stuff like that. There is recently another kind of imaging called brain connectivity fMRI. So it actually shows circuits as you are doing something. It shows the circuits in the brain and how these circuits light up and how they make a certain function possible. So now we're going to survey respiration. Respiration, you say, what does it have to do with speech? We know that, for example, a car, when the car moves, it has to have power, it has to have energy. You give it gas. Without gas, these cars we know today do not run. Maybe they will invent other ways, but air to us is the same as gas is to a car. We inhale to live and to survive, but we learned how to adapt the system so we can produce speech. So we inhale, and then as we exhale, we use the pressure that is going out and the air as it's going out. We close it because it has to go through between the vocal folds. We close the vocal folds, you can like this, and then we trap the air, and then we chop it. We make a buzz, and then the buzz goes through so we can articulate that. So respiration is the process of bringing in air into the lungs for the purpose of extracting oxygen and disposing of carbon dioxide. We get oxygen for our body to survive, and we expel carbon dioxide, which is a waste. In order for us to get air in, our lungs have to expand. And in order to expand them, we have to use muscles. The diaphragm is the biggest muscle for inhalation and exhalation. And when it contracts, it goes down. So it expands the thorax. When we say the thorax, the chest, and inside of it, the lungs are also expanded. So it expands the thorax vertically, and it creates the biggest amount of expansion. And then at the same time, the thorax itself is elevated, and as it's elevated, it is pushed out and sideways. So it is expanded transversely and anteriorly. So this way now we have expanded the thorax in 3 dimensions. And now as we expand it, the pressure inside of the lungs decreases, and it sucks air from outside until the air inside of the lungs becomes the same level of pressure as the outside. We call that equilibrium. So the lungs are surrounded, of course, the thorax encases the lungs. And the thorax has 12 ribs on each side. And each rib is connected to the vertebra of the vertebral column. So 12 ribs, the top 7, they are called true ribs because they are connected both, to the spinal column and to the breastbone. That is called the sternum. And then below the 7th rib, you go 1, 2, 3, 4, 5, 6, 7, and then you go 8, 9, and 10. These are called false ribs because they don't have a direct connection to the sternum. They kind of combine their cartilages together, and they kind of connect onto the cartilage of rib number 7. And they have some kind of connection, but indirectly. So we call these the false ribs. And at the end, there are 2 ribs that are they're not connected to the sternum at all. They're just hanging there short. And they are called the floating ribs. And that is because of these 2 ribs, we are able to bend down, to rotate or go around like this and bend down and stuff like that. So these are the ribs: true ribs 7, false ribs 3, floating ribs 2. The way that the respiratory system works, we are going to speak about how the gas exchange is in the lungs. But look at, for example, see how the diaphragm is positioned, like a bowl, inverted bowl, and it sits under the lungs, and the lungs kind of stick to it because of there's some kind of connection called the pleural linkage here. Kind of they stick like you have 2 pieces of glass stuck together. So whenever the diaphragm goes down, it pulls the lungs with it and to inflate them. when we speak, when we breathe, most of our breathing is performed by the diaphragm. It goes down and up. We exchange like a half a liter on average, a half a liter of air, compared to being able to have like 6 liters or 7 liters of air inside of our lungs. This is, our lungs are able to, depending male, female, but on average, a human being is able to hold, to take, in about 6 liters of air, for example. So, but as we breathe, we take in and exhale a half a liter. But when we exert effort, like I'm speaking now, I am using more. And I'm using the diaphragm and a group of muscles that are called the assisting or the accessory muscles of inhalation. All these muscles, they enable us to elevate the thorax and expand it and hold it until, it fills up with, the lungs fill up with air, and then we achieve inhalation. So the idea of Boyle's law, how it relates to breathing, how it relates to respiration. You need to know what the words say, what Boyle's law exactly says. And you need to focus on the word enclosed, closed. So Boyle's law says, the volume of a closed container, when the volume, the space inside of a closed container increases, the pressure inside of that container decreases. And when the volume of a closed container decreases, then the pressure inside of that column increases. Okay, you need to know exactly what the words say, and if you leave the word closed out, then you didn't answer the question. Because without saying closed, it doesn't mean anything. So now, and how this law relates to inhalation and exhalation. In inhalation, in order to inhale, we have to expand the thorax. We have to expand the volume of the lungs. When we elevate the thorax and bring the diaphragm down, we create a larger volume. What does that do? What is the next step? The larger volume is going to, it means, because our lungs are an enclosed container, when we expand them, the lungs, it means we create negative air pressure. It means that the air pressure is going to decrease. Now, when it decreases, that creates suction, and that means it will suck. Now, this is not what, this is how it works. Now, that suction is going to draw air from outside, and the air will continue to flow until the pressure inside of the lungs is equal to the pressure outside. That is called equilibrium. So until the point of equilibrium is reached, and then the inhalation process is halted. How does Boyle's law relate to exhalation? Okay, now, in exhalation, the beginning of it, the muscles that are holding the thorax up and lifting it, they relax. The thorax collapses, goes down by gravity. And then the ribs are going to be twisted back in and down, and they come in and down, and they compress the lungs. The diaphragm rises and also compresses the lungs further. All of these, and the abdominal muscles push in. So all of these forces are going to narrow the volume inside of the lungs. Now, when we decrease the volume, what happens? The pressure inside of the lungs is going to increase. Now, what happens after that? That is going to push the air out of the lungs, and the air will continue to stream out until the point of equilibrium is reached again, and the process is halted, and then inhalation will begin again. So you need to know what the exact words of Boyle's law, word by word, and then you need to explain how it relates to inhalation and exhalation. So in exhalation, there are forces, passive forces, that enable us to, it will make exhalation easier. For example, you can think about inhalation as, bringing a rock, a big boulder, rolling it up a hill, bringing it up, putting it on top of the hill. So you put effort as you push, and bring it up. Now, if you want to send it down, all you do is to just push it, kick it, and it's gonna just go down then by its own. And it will roll down its gradient. So there are three forces, natural forces, that will make exhalation easier than inhalation, because in exhalation you are reaping the benefit of the work you did before when you were inhaling. For example, elastic recoil. When you are inhaling, you are lifting up the thorax, and the diaphragm is contracted going down, pushing on the abdominal viscera, abdominal organs, and the abdominal organs are pushing on the abdominal muscles, making your stomach go out. So then, when you exhale, you get elastic recoil. That is the elasticity that will bring back the structures back to where they were. For example, the abdominal muscles that were pushed out, they now come back again to where they were because of elasticity. Elasticity means you pull something away or distort it, let go, it will bounce back to shape. Now also, the diaphragm, when it is contracted like this, elastic recoil is going to make it bounce back up again to rise like this again, which to compress the lungs again. Elastic recoil is going to make the internal intercostal muscles kind of bounce back in and down to bring the thorax back in and down again. So elastic recoil enables the muscles that had been stretched, had been activated in inhalation, to come back again and regain their shape, to come back again, become smaller, and to compress the lungs and make the volume less. So for speech, again, speech breathing is effortful. It is effortful. When we are breathing quietly, not speaking, not doing effort, the cycle of inhalation, exhalation, that makes one breath, one inhalation, one exhalation. That's one cycle. The inhalation part, it makes about 40 to 40%, 45% of the cycle in terms of time. So let's say, for example, if you give both an inhalation and exhalation 10 seconds, then 4.5 seconds are going to be spent in taking the air in. And 5.5 seconds will be taken in exhaling that air, expelling it out. That is natural rest breathing. For speech breathing, if the cycle, the whole breath takes 10 seconds, only 1/10 of that is going to spend in taking the air in, and 9/10 is going to, 90% of the time will be spent in expelling that air out. It's like taking a balloon and blowing, and then holding the neck and trapping the air and holding and releasing the air, the air, so that the balloon makes a sound. And the balloon is going to continue making that sound for a long time. So again, in speech breathing, the cycle of breathing is different. The inhalation process takes about 10% of the cycle, and 90% is spent in exhalation, and this is because we close the airway, and as the air is exiting, we phonate and make speech. And now, phonation is the process of making sounds, the process of making a voice, making a voice, a buzz. And that is made by the larynx. So the larynx is made out of primarily cartilages, except for a single bone here that sits on top of the larynx. And that bone is called the hyoid bone. So the larynx has five major cartilages, and then it has two pairs of smaller cartilages that you'll study. It has many muscles that regulate vocal function, and also many muscles that lift up the larynx and drop it down, pull it down. So the larynx has three major functions. One is protection of the airway. So you can think of it like it has the vocal folds, just like all the air that you breathe has to go in the larynx, between the vocal folds. All the air you exhale, it has to go between the vocal folds. So protecting the airway, serving as a valve, and also enables us to phonate, to make sounds, and also to be able to push, for example, lift. In order to push and lift, you have to close your vocal folds tightly, hold your breath, and then you can lift. You can swim, dive by holding your vocal folds together and shutting the airway. If you take this larynx and split it right here along this way, it will be like this. So now you have one vocal fold here, one vocal fold here. When they come together, they close like this. They open, they go like this. These are the true vocal folds, the ones that vibrate to make our sound, speech, our voice. There's a video here. It would be good if you watch it, because there's no reason, you can watch it better on your own. And on top of the true vocal folds, there are two folds hanging down here that are called the ventricular folds, sometimes called the false vocal folds. So these are the functions of them is to hydrate the vocal folds, to make mucus, and make them slippery, make them moist all the time, to provide protection, and under extreme conditions to enable us to close the airway also. So they provided another layer of protection. So the process of bringing the vocal folds together to close them is called adduction, like adding them up. The process of bringing them apart is called abduction, like taking them away from each other, abduction. And the space between the vocal folds, the space between them is called the glottis, To differentiate that space from the space between the false vocal folds, sometimes you call this the rhymoglottis. But when you say glottis by itself, it means the space between the true vocal folds. This is just the muscles of, if you look from above at the larynx, you will see these structures. Of course, this area is closed by, membranes here, and only this area, the glottis, is open. But this is to show us the anatomy of the real vocal folds. The real vocal folds, the true vocal folds, each one is made up of two strands of muscles, like my fingers. This is called the thyrovocalis muscle, next to the glottis, thyrovocalis. And that is the muscle that enables us to vibrate to make speech. The muscle next to it, that is also part of the vocal fold, it is called the thyromuscularis. Remember it from muscular. the thyromuscularis. So both of these two pieces make one muscle called the thyroarytenoid, which means the vocal fold. Thyroarytenoid is the anatomic name of the vocal fold. The thyroarytenoid muscle, the vocal fold, is divided into two little strands of muscles. One is called the thyromuscularis, the other one is called the thyrovocalis. The way to bring these vocal folds to the midline, so to close them, to bring them so that they can trap the air and vibrate, is done by two pyramidal structures here. You can see parts of them. These are called the arytenoid cartilages. Basically, each one of them is connected with, say, a vocal fold like this. So you imagine there's one, and the other one, is connected, and the vocal folds in the front are together. So, but when you have the arytenoid, say like this, and if you rotate the arytenoid, you're gonna bring the vocal fold to the midline. Rotate the arytenoid the other way, you take the vocal fold away. So each arytenoid is connected with a vocal fold. And there are muscles that rotate the arytenoid to bring the vocal folds together to adduct them, and there are muscles that will rotate the vocal fold, the arytenoids away to take the vocal folds away from the midline. So again, the thyroarytenoid, it means that muscle here, the two pieces of it. And this piece is called the thyrovocalis, this piece is called the thyromuscularis. The posterior cricoarytenoid, that muscle here in the back here, not sure if I have it. That muscle in the back here is a muscle that abducts the vocal folds. It rotates the arytenoid cartilage, and that swings the vocal fold away from the midline. When you do this one and this one, you open the vocal folds. There's the cricothyroid muscle. Cricothyroid, that is that muscle here, cricothyroid muscle. When this muscle contracts, it shortens, it takes the whole thyroid cartilage and pulls it forward and down. So let's go back here. So now here, see the vocal folds here, both of them are connected, originate inside of that thyroid cartilage. And from the outside and below, you have the cricothyroid muscles. So the cricothyroid muscles, when they contract, they pull the entire thyroid cartilage forward and down, and when they do that, they pull down the vocal folds with them. So in effect, you stretch the vocal folds. When you stretch them, you raise their pitch. You make them vibrate at a higher pitch. Like, hi, how are you? You can do this because you can, contract that muscle, and they elongate the vocal folds, increase their tension, and they vibrate at a higher pitch. So that is the cricothyroid, responsible for raising your pitch. And then the intra-arytenoid muscles means in between the arytenoids. If you look carefully here, you have one muscle that goes from side to side between the arytenoids. That is called the transverse arytenoid. And there's a muscle that goes like an X, see? Like an X here, right behind it, like an X. That is called the oblique arytenoid muscle. So these two muscles are the intra-arytenoid muscles. They enable us to compress the vocal folds and to hold them so we can hold our breath for longer. The intra-arytenoid muscles. And then we have the lateral cricoarachnoid muscle. This originates on the side of the cricoid cartilage here, and it inserts onto the base of the arachnoid muscle, cartilage I mean. So when this muscle contracts, it swings the arachnoids inward to the middle, to the midline. So the lateral cricoarachnoid adducts the vocal folds, closes them by swinging each arachnoid to the midline. So this one swings this one to the midline, and this one swings it to the midline. So the lateral cricoarachnoid closes the vocal folds. The intraarachnoids compress and help in closing the vocal folds. And the only muscle that is responsible for opening them up, for abducting them, is the posterior cricoarachnoid. One here and one here. So when we speak about, how do we speak? So there's a theory called the aerodynamic myoelastic, theory of the vocal fold function, and that basically says that in order to phonate, you need to abduct the vocal folds. You bring them close together. And when you bring them close together, as soon as you close the vocal folds, the air pressure is going to build up beneath them. And as it builds up beneath them, it's going to push them up, it's going to push the medial edges apart. So they start to go away like this, to be abducted. And then the vocal folds would want to come back again to close, to resist the air pressure. And then the air pressure goes back again, to open them up. So how it goes first, as soon as you close the vocal folds, the elastic force of the vocal folds, because they are comfortable in the closed position like this, they want to come to the midline. When you bring them away, they want to come back to where they were. So the elastic force of the vocal folds is 0 when they are closed. That means at the same time the pressure beneath them is strong. So that means the pressure beneath is going to overcome the edges, the thin edges of the vocal folds, and push them away. So then, when you push them away to the maximum displacement, the pressure is released, and then you don't have enough pressure. So the elastic force of the vocal folds is going to bring the vocal folds down again, start to swing them back again to rest, to the midline. As they come back again, the pressure increases again. So at some point when they are close enough but not fully closed, that creates a constriction, and that is going to make an area of negative pressure, decreased pressure between the vocal folds. And that creates something that we know as the Bernoulli effect. Basically, the Bernoulli effect causes the air pressure to be lower between the vocal folds, and that will suck them together to close the vocal folds. And then when they are closed, the pressure builds up to maximum beneath them, and it pushes them again away. And then the cycle keeps going back and forth, back and forth. So as I'm speaking now, I'm making approximately 115 cycles per second, as a result of that. If a female speaks, she makes about 225 cycles in one single second. Vibrations like back and forth, back and forth. So when we study different aspects of phonation, we look at the frequency of the voice, or the pitch of the voice. Pitch is determined by the thickness of your vocal folds, by the length of your vocal folds. For example, a man's vocal fold is massive, has a lot of muscle in it, and it's big. that makes it vibrate more slowly compared to that of a child, compared to that of a female. And then, so tension, when you have a vocal fold that is more tense, it will vibrate faster than a vocal fold that's less. But let me take my own vocal fold. If I want to make it higher pitch, I'm going to increase the length of it, and that will increase the tension of it, and that will make it, will make it vibrate at a faster rate. Intensity means the force, or loudness of the voice, and that's what we describe. We study loudness, and how loudness is a function of how much air you have in your lungs, how much air do you expel, through between the vocal folds at a given time. When you raise your voice, you allow more air to go between the vocal folds. So articulation, you just have an idea about. Okay, almost done. So articulation basically is the process of bringing two or more oral structures of the vocal tract to make sounds, one sound or more sounds. And the articulatory system includes the oral cavity, nasal cavity, and the pharynx, for example, here, and the oral cavity and the nasal cavity, which we call it the vocal tract. Then the area that is between the nasal cavity and the oral cavity here, between the velum and the back of the throat here, that is called the velopharyngeal port, or the velopharynx sometimes, but better call it the velopharyngeal port, because when you elevate that velum, lift it up, you separate the nasal cavity from the oral cavity. So whenever you say ah, that is lifted up. All the vowels, most of the sounds except for the nasal sounds, the velum is up and closing the nasal cavity, closing it off, and making the sound, the air go out of the mouth. So that area that's called the velopharyngeal port is the area between the velum and the posterior pharyngeal wall. The pharynx is the vertical tube that is empty, that has air in it, that extends from top of the larynx to the back of the nasal cavity, and that has the hypopharynx, oropharynx, and nasopharynx. So that nasopharynx is another name for the velopharyngeal port. The vocal tract, of course, has the teeth and the lips, and there's an area when you say t, d, l, all these areas, this area t, d, s, z, l, and n. The tongue tip touches an area that we call the alveolar ridge, and these 6 sounds are called alveolar sounds because you produce them by contact between the tongue tip and the alveolar ridge. And then you have the soft palate. Another name for it is called the velum, and it is important for swallowing and for speech and for the quality of your voice. And then the mandible, of course, is another name for the jaw, and it has a lot of muscles to move it up and down, make it do its function. And it enables us to articulate. And the tongue also it's made out of a bunch of muscles that move it around and up and down. And we study all of these structures in detail. We shred them in anatomy, and we know the function and the anatomy of them. In terms of what resonance, basically it has to do with how the vocal tone that you make in by the vocal folds, how it travels through the pharynx, through the oral cavity, nasal cavity, and how the air inside of the space vibrates to echo the sound, to repeat the sound so that the sound doesn't die down before it gets out of your lips. So these echoes or repetitions of the tone that is made by the vocal folds, these are called harmonics, and they are basically, they keep the sound continuing even though if the vocal folds stop, after they make the tone, that the harmonics enable that sound to be continuing to exist in the air until it exits, and then the air, it becomes an acoustic signal that the air can carry out to another person. The vocal tract is known as a quarter wave resonator, as a system that amplifies the tone that comes by serving as a filter, by taking out elements that can oppose the sound wave and enhance and amplify signals that are good, that will make the sound louder. When we speak about speech sounds, there are 43 English sounds, and we have 14 vowels and the rest are consonant. So we describe a consonant using three words, and these consonants, and then vowels, we describe them using 4 words. We mentioned that before. So the 3 words we use, or the criteria to describe consonants, are first voicing, and then placement, and then manner. For example, take the sound p. When you say p, your vocal folds do not vibrate. So we call that sound voiceless. If you want to see if the vocal folds vibrate, say instead of p, say b, b, b. When you say b, your vocal folds vibrate, but say p. So p is a voiceless sound. And then where is it placed? Made. Say the lips, 2 lips together come and make it. So say bilabial. So voiceless, bilabial. And then what kind of sound? The manner of it. What does it sound like? Oh, it's a stop. You stop, you block the air completely, and then pop it. You release it. So p becomes a voiceless, bilabial stop. And we looked at the sounds. So use these criteria to describe any consonant at all. For example, it's a voiceless, labiodental, and then means fricative. So these are just ways to describe a consonant. To make every consonant is going to have unique description. And vowels, we describe vowels using 4 criteria. We say, for example, is a low, back, tense, unrounded vowel based on the tongue position. Is the tongue up or down? Is the tongue advanced in the oral cavity, or is it back? Is the tongue are the lips rounded or not? And is the sound, does it require more muscular energy, means tension or not, tense or lax. We also look at a vowel in terms of formants. Formants are the resonances that occur in the vocal tract. And the first formants, the 3 that are the loudest ones that combine together to make the sound loud and amplified. They're the first one, first, second, and third. And then we have the vowels also. We classify them into monophthongs and diphthongs. For example, most of them are monophthongs, single vowels. So you say a, e, these are single vowels. But if you say I, they become a diphthong. A diphthong, there are 5 of them that basically two vowels blended together, like O, E. So oi becomes a diphthong. If you say a, becomes a diphthong, like man, like hey, may, a, that's a diphthong. So anyways, a diphthong consists of two vowels that are merged into a single one, and there are 5 of them, and the rest of, and then we have 13 vowels. In speech production, we also study suprasegmental aspects or features. We study loudness, speech loudness, pitch, duration, like how long this, the speech, the words and the sentences take, and so on. And then we look at to understand the way that we phonate, for example, and how that buzz becomes, speech. Basically, there's a theory called the source filter theory that explains for us how this whole process, how phonation is connected with articulation. So the vocal folds are a muscle that has a cover. It has a cover, and that cover is very thin and stretchy and rubbery, and the air pressure pushes it away from the center, from the midline. So that is the body of the vocal fold. Is covered by a what do you call it? An epithelial layer, and then so that vocal folds generate a buzz. That's the source tone. The original tone comes out of the vocal folds. That is the source. And then, as that buzz comes out into the vocal tract modifies that buzz by eliminating certain parts of the sound wave that can interfere with it, and leaving and amplifying the parts that are good in the wave, that can maximize the loudness of the sound. And then that is gonna, as that buzz goes out, then you chop it and articulate, and that into speech. Co-articulation is the process of producing 2 or more sounds at the same time, basically. Two sounds at the same time. For example, when you say key, you are getting ready to say E, but at the same time, you are making the K as you are making K, but you are giving it the characteristics of the E by retracting your lips. So it requires a lot of motor coordination, co-articulation. So in this, again, we looked at the highlights of the nervous system, and we looked at the cerebral cortex and the cerebrum in general, and how it consists of 2 hemispheres and different parts of the cerebrum. We said the cerebrum has gray matter, which is the cerebral cortex, and it has white matter, which is beneath the cerebral cortex. And there are different areas. The right hemisphere does different functions than the left hemisphere. And we spoke about areas that are important for speech, including Broca's area, Wernicke's area, and the pathway that connects these two, called the arcuate fasciculus. We spoke about the motor movement and how it's mediated by the pyramidal and extrapyramidal tracts. And we kind of sampled some of the nerves, the cranial nerves that are important for speech and swallowing and communication. We looked at respiration and phonation and articulation, and then just looking briefly, very briefly, at acoustic characteristics of the vocal tract and how it enables us to transform that buzz into speech and to amplify that buzz. So I hope that you found this detailed enough, I know it is long, but I hope that that you find it helpful. You can always go back to it. Thank you.